Hey guys. Okay, let's see here. Trying to double check and make sure I know where we left off, which I think was at TCP fast retransmit. Yeah, it looks like it. Okay. Let me pull that up and get us right back into the thick of that. Two of these I can't really load that way, so let me try a different way for those. There we go. Okay. Yay. Good grief, what happened with that? Let me get to exactly the right slide. This presentation has 260 slides, but only because it had tons of animations and they got split up into a bunch of different slides so they could be uploaded easily. All right, I think I'm ready to go. Excellent. My plan is working perfectly. My hands never left my arms. All right. We had left off last time when our Caped Crusader was trying to do the three-way handshake, which sounds like some secret fraternity thing or something, but I wouldn't know anything about, I'm sure. But what we see on this slide, and we talked about a little bit last time, was it's one of those situations where it's actually a big payoff if we can draw one finite state diagram on the same page for both the sender and the receiver. It's sort of a foolproof way of guaranteeing that neither person kind of gets off the track. You're not both in the same spot at the same time, right? So you're in different positions, but at least you want to know that you both start at the same spot, you both arrive at establishing the connection at the same spot, and you both close the connection at the same spot. So that's an exception when it pays off big if you can draw this like as a single diagram. It's hard, however. So we will admire the way this one looks and maybe walk through it a little bit and then move on with our lives. With TCP, we talked about how you need to be sure when you open a connection that you don't somehow misinterpret one person's message for another, or if it gets duplicated, you don't think they're trying to open a connection twice, or you don't get somebody else sticking their message in the middle trying to fool you. So we did things like come up with random sequence numbers to use, making sure we increment the acknowledgement numbers in a very specific way, handing things back and forth, setting bits in the header, just so we can be certain of where we are and that we're both agreeing to open up a connection. Same thing happens on a close. So when closing a connection, either side can close it. So there's a concept of who picked the fight first. And we talked about this in terms of security before, where if you're sitting inside of U of H, and this is the big bad outside world with people trying to send all sorts of attacking packets at you, you can still be a little lamb and open up a connection to the outside world. But because you opened it, the gear recognizes that and will send data back and it will let it through. Whereas on the other hand, if you're sitting here and somebody just tries to initiate a conversation sending data in, that will never be allowed. So direction makes a big difference, and that's true with TCP as well. So you have your client who opened the TCP connection and the server who accepted it originally, and you both are going along down your timelines, and one of you decides you've had enough. So you can send a message to the server saying, you know, I'm done. That's all for me. And the server will say, well, that's great, but I still have things in my buffer that I need to send to you. So you can enter a state where you're not going to send nothing else, where you'll be silent, but I can still send things over to you. And then when I'm done, I'll let you know. Okay, I'm done too. And once that happens, now you both agree you're in, complete done. So you'll both enter this state where you'll wait a certain amount of time to make sure it's twice the amount of time a packet would normally take, twice the round trip time. Let me get rid of one of those T's. That's a little too much. You'll wait to make sure if there's any last straggler data that maybe was sent here but took a while to get here. You've already closed things off, but at least you'll dump it on the floor. You're not going to leave it floating around the network for the next person to inadvertently pick up as a message that they think maybe was intended for them, whoever follows you with the next client connection on here. All right, so you can do that in both directions. So looking at closing a connection, I say I'm done. I don't want to send anything else. The server acknowledges that, but says I still have a little bit more to do. He can send some more things in here, and then says, okay, I'm done as well. Now you're going to wait twice the lifetime to make sure any straggler data comes in. So that's the idea of doing a very clean close. Now, this doesn't look at all obvious or intuitive. That's because it got beat into us the hard way from not having enough protection and safeguards and getting caught with messages showing up that got misinterpreted by somebody, by somebody later. Bad things happen. Okay, let's transition now to one of the most important topics in networking, which is congestion control. Congestion control deals with how does TCP, whose software is only running on the two ends of a connection, never on the routers in the middle. So you have a device here and a device here, and they're talking to each other with TCP, and all the routers and all the other devices in the middle, they aren't running that. So you're coming down, you're going up to layer 3 only. You only have layer 5 running at the two ends, layer 4 running at the two ends. How does TCP hope to have any prayer of knowing what's going on the network and avoiding situations where it causes catastrophe by letting these routers get so full of their data that they overflow? Now remember, TCP tries to be nice about this. It wants to check and make sure it's not overflowing things. So how exactly is that supposed to happen when you aren't even running software that you can talk to? There's nothing to communicate with down here. So the answer is through some interesting hints and tricks and clues. I feel like a little bit like Scooby-Doo doing this. One of the things that you notice that can happen that we've talked about a little bit is you can see that you are sending packets over, but you're not getting acknowledgments back. Well, that could mean a few things, but one of the things that it could mean is congestion. So you have to decide if you've got enough data to make that decision, and if not, opt on the side of caution, err on the side of caution, and assume that you're causing congestion. So we're going to talk about that in some detail. The other type of thing that can happen is if somebody starts to get full, they can add it to a packet that's being sent along, and when it gets over here, they can say, hey, complain back at this guy and let him know that you're killing me here. I'm dying. You're overwhelming me. So there's some other mechanisms to do some things like that where routers can set some bits to try and ask for help from the receiving end to let the sender end know that, knock it off. Okay? So it's sort of like a Stephen Wright joke a little bit in that regard. All right, so congestion control basically is caused by the need to deal with too many people sending too much stuff that the network can handle at any given time. It is different from flow control. Remember, with flow control, which we also looked at, you are telling the receiver is telling the sender, here's how much space I have left in my walk-in cooler for you to ship me more vegetables. Don't put a truck on the road that has more stuff than I can handle. So we saw this when we looked at packets, and I'm going to do that right now for you guys. And I'm going to try to open up some other programs and take a look at other things going on. And we're going to find some interfaces here. And I'm going to grab some things, and we're going to go here, and then we're going to go here. And I'm going to open up some other stuff, and we're going to try to convert some things here. And we're going to look at the New York Times, and we're going to look at the Chronicle. We're just going to have ourselves a grand old time here. And I'm going to open up Dropbox folders, and just going to make people miserable on the network, just causing a tremendous amount of of stuff here. And then I'm going to, just like that, I'm going to stop. So this network is in deep doo-doo. And in fact, it's still not done showing the packets, even though I stopped grabbing. Is it finished? Yeah, so I think it's like totally, I think I totally overwhelmed this poor guy. Tons and tons and tons of packets that have issues. It's just horrible. What is going on? Am I even transmitting? Can you guys even hear me? Check. Oh, I know what's going on. All right, so this I can fix. I need to turn checksum back off again. Stop it. Stop it. Validate. Checksum. If possible, do not do that. Okay, that should make lots of people a lot happier. Lots of things go away. All right, so the reason I did this is I wanted to come up here and pick a variety of packets and show you, for TCP specifically, window sizes. I got to get my window sized right. Okay. You willing to work with me now? You sure? Right. Window size, 2098. It's now gray. As I scroll through, you can see the window size changing. With every packet, it changes. Do you see that? Some of these are not regular TCP packets. They're encrypted, so they don't quite look the same, but the rest of them, they're all over the map. So that's flow control, okay? Letting the other side know how much space you've got. Congestion management, congestion control is not that. It is not flow control. So one of the ways you know that you have congestion problems is packets are lost or there's long delays. And it's a huge issue. It's a topic of great study. So what are causes of congestion? Well, two people sending too much at the same time. So we're going to use this nomenclature of a lambda variable to show the amount of data that we have been entrusted with sending by the application layer. So lambda n is not the name of a hotel in San Francisco. It's the amount of data that you are being asked to send. But we know there's going to be some retransmissions, so the actual amount of data that you cause to be sent over the network is greater than lambda n, as we'll see in a moment. But ideally, if there's no congestion, there's unlimited shared output link buffers, you never have to drop something because there's not enough room to send it, then you can have lambda out equal to lambda n. So in a perfect world, you get the lambda n goes up as lambda out goes up, and you reach a perfect state where you have exactly 1/2 of the connection that belongs to you, and 1/2 belongs to the other host that's shown on this diagram, which in this case is host B. Delay increases, and I do need to kill off Wireshark. It looks like it's just wiping out my laptop's performance. It's not even able to save this this PowerPoint, although it is 260 slides long, so I kind of get that as well. But let me see if I can quit out of a couple of things here. Make life a little bit better. Can't wait for the new Macs to pop out. Can't wait. Just cannot wait. All right, here we go. And I see that my delay goes up as I get closer. We saw that with our delay estimator that you saw on the exam, but it goes up to infinity as I start getting closer and closer to my share of the data. But what in the world is going on back here? This is a stupid Chronicle pumping video into my screen. Stop doing that, for God's sake. Okay, that's what's going on my CPU. So the delay goes up, the buffer's still up, but I have infinite buffers. So wouldn't that be nice if we could count on something like that? Scenario 2, you have finite buffers, so things get dropped. So the things that you retransmit add to the amount of data. So instead of just having lambda in, you actually, it's as if you were given more data than you really were to send. Lambda prime is in. So this lambda prime, which they leave off the prime here somehow, that's actually greater than or equal to lambda n. Okay, but we're still pretending that we have perfect knowledge of what's going on, so we know when the buffers are full and we won't send anymore. Maybe something gets dropped that as soon as that happens, we're clued in, we're aware of it. So that would still let us get up to kind of the maximum pretend amount here, but known loss, if you have that, then you know also when it's time to retransmit something. You don't have to wait for acknowledgments to come and figure it out and piece it together. You know when something's been dropped because you have perfect knowledge. Well, we don't have that either. So if something gets dropped here, we can pretend like we know it. And ideally, however, we start to see this asymptote. Why? Because we can never really reach this R over 2. Because we need to reserve some of the bandwidth in here that would have let us have our full share of the network, in this case half since there were 2 senders. We need to reserve some of that for retransmissions when the buffers get full and things get dropped. So we're going to pull down a little bit our ability to send all that. And this still ignores the delay. It's still infinite delay if you get this close, if you push the limit. But at least now I have finite buffers, and when things get dropped as a result, I know to resend them. We also can have some duplicates that take place as well, and that's just part of the issue with the network. Things can time out prematurely. Your timer will give up, especially if you allow very, very long delay, and you're doomed to resending a packet twice that you don't need to. So that also pulls down the amount of bandwidth that you can get. So as we mentioned a little bit last time, the sad part about this is that there's a huge penalty for retransmissions. So let's say I'm a PC here and I have all of these routers in between me and the destination. All right, and here's my destination over here. So my packets make it through fine, all the way through to almost the end. They get to here, and the packet gets dropped. So how much work has to be redone? Am I going to be resending one packet? Well, one way to look at it is that way. The worst way to look at it is this guy is doomed to duplicating the amount of work he did, and every one of these other routers are also doomed to duplicating the work. They did their job right. They got the packet through. They got it closer to the destination. This clown dropped it at the end and doomed everyone else to duplicating the amount of work that they had to do by resending the packet again. So it's extremely costly to have packets get dropped. On average, they'll be in the bottom half of the connection. Half of them will be there as much as on the top half. So they'll be dropped at the halfway point, in other words. So it can be costly. So some of your link's going to have to be dedicated to that. So we really want to try to minimize this if we can. Here's another scenario of congestion. 4 hosts, each of them have a connection to the other, but in a different pairwise arrangement. So A connects to C, B connects to D, C connects to A, D connects to B. So they all share one router in the middle. So as D goes to B, he passes through this router and this router. And in this link, he shares it with A. So A and D find themselves next to each other for part of this journey, trying to get to different places, coming from different places, going to different places, but they share this router in the middle. So now it's super tricky because you can't even monitor what's going on at host B and have confidence that you're not going to overwhelm the router, because the other guy, he didn't even go into host B. He couldn't care less. A's going to C, D's going to B, but you aren't. A's not. A's going someplace else. So this is a very realistic type of problem. You have a full dispersion of pairwise connections and multi-hop paths. So everybody arriving at this router is going to have to kind of fight over what's going on. And that becomes fascinating to manage in terms of queuing theory and buffering. So when a packet is dropped, any upstream capacity used for that was wasted. That's what I just showed you over here with this diagram here. So you want to try to minimize, and at some point you start retransmitting enough that your bandwidth continues to the right, your bandwidth continues to be consumed with packets, but not only are you not sending anything more into the network that the receiver can get out, In other words, this caps off. Let me draw this, copy this over here and show you, because I'm dying to kind of scribble on this a little bit. Right, so what this diagram represents is this is what the sender is sending up until their fair share, which with 2 senders was 1/2 of the network. This is what the receiver is receiving. Now you'll notice this is lambda out and this is lambda prime in. So what this lambda prime includes that lambda did not are retransmissions. So you can get busy, and some of this is retransmissions. And that you can set up this case where a greater and greater percentage of what you're sending, like from here to here, is retransmissions. And so if you look at the percentage here of data that the user actually wanted once and duplicated that you were forced to resend, that looks like that. Over here, it's backwards. There's very little new stuff for the user. Most of this stuff is retransmissions, duplicates in here. So as you look at what the receiver is getting, they start getting new stuff for a while until maybe at some point you get here and where the volume of new stuff starts to go down and your rate of new stuff is going down. So you're getting less and less. Most of this is duplicates, and it just collapses on itself. You're using all of your bandwidth. Nothing new is being retransmitted. It's so congested. It's all just retransmissions that never make it to the other end. And so you retransmit them again, and they drop again, and on and on and on. So that's when the network collapses. And it's easy to do, and it doesn't take long. So what we want TCP congestion management to do is come up with some scheme where we see that this is beginning to happen and react immediately. And so what TCP congestion control tries to do is something called additive increase and multiplicative decrease. This is where you inch your way forward, and if you see there's a problem, you run quickly back away. So this is like a kid who's supposed to be in bed on the 2nd floor. Parents are having a party downstairs, and so the kid just cannot stand the suspense. This would be my son. So he sneaks out of the bedroom and tiptoes his way carefully to the edge of the stairs and peeking down there, and very gregarious, wants to come and meet people. So he's sort of inching his way down, and the other guests, they started like, oh, hey, look, it's what's his name, and hey, how you doing? And they're trying to be friendly, and the parents have given strict orders that you're supposed to be in bed. So this goes on inch by inch until the parents catch you. And then the parents are like, back upstairs into the room, and you turn around and you run back, or you do that even when you think they've caught you. So TCP acts a lot like that. So the approach is that you slowly increase your transmission rate, and you do that by growing your window size. What you're doing is probing to see if the bandwidth situation has improved. Maybe you've rerouted over a bigger network. Maybe other people have taken a break. Maybe other people are slowing down. Maybe a problem's been fixed. But at any moment, more bandwidth could be available. So you are constantly probing. You are constantly trying to increase your transmission rate up until the point when a loss actually occurs. However you conclude that the loss has happened. A timeout goes off. You see 3 duplicate acts. Somebody hits you upside the head, whatever it might be. So the way additive increase works is you increase your window size by 1 packet, by 1 segment for every round of transmission until a loss is detected. And once that happens, you cut the window in half. You saw it in half. So this is kind of what it looks like, if I can get it to draw for me. So you start by growing incrementally, by growing linearly. And if there's a drop packet, a loss, you cut it in half. You continue to grow linearly again. So just to make this clear, looks like a stupid thing's going to try saving again. So let me, looks like I always have. So we use lambda count. No, not exactly. Okay, let me try and draw on this because I think it's trying to save it out again. And it's going to drive me crazy. Okay, so this is around round 2 we had a loss. We go back down to half of what we were. Each round we grow incrementally, so this could be very, very many rounds. And we get to the point where we have another loss again, which it should show me here. There we go. We have another loss, and then we grow again. So this is also called a sawtooth diagram, because if you've ever paid close attention to the edge of a saw, it has diagonal lines and vertical lines, and diagonal lines and vertical lines. And so hopefully it doesn't quite look like this. This saw would be in big trouble, but you kind of get the idea. So that's a very sort of, I don't know what sort of demographic they thought they were appealing to with that sawtooth analogy, but you have to explain it to most people because most people don't use saws. Why would we? So that's what that sometimes is called. So you cut it exponentially and you grow it linearly. So linear increase and exponential decrease. All right, so back to our window. Some of the congestion control details. I have my window size, I have my variables, and I've sent the things that are in yellow. They have been transmitted, but they haven't yet been acknowledged. And I'm constantly checking to see if I have more space in my window. If I have more space in my window and I get more packets, I will send them. So what happens if there's a loss? What happens if there's a loss is I cut my window size back. So it's going to change the results of this formula immediately. Usually it means I can send no more. I have to wait a while for acknowledgments to come back. So what this does on average over time is, believe it or not, it guarantees that your congestion window size divided by the RTT, you basically are going to send a whole window at a time and then wait for an RTT and get some bytes back. So we call this the burst dump nature of the way TCP works. So if I were to draw that for you, which is going to be apparently very hard for me to do, you will find that you dump lots and lots of packets out, and you fill your window. You can send no more, and now you need to wait for acknowledgments to come back. And because round trip time dominates your network performance on long haul networks, you're going to be waiting a while before you send stuff. Once you get an acknowledgment, the acknowledgments come back quickly. They come back in a burst as well, and then you can send things as you've got going on. We saw this. We saw this with our very own eyes with our animation. And it wasn't with this animation. It was with this animation. Send. Well, it stopped me after sending 5, so there's no point in continuing to click. And as these things come back, I'm going to continue to hit send. Send. And you can see what happens. I've constantly got stuff to send, but until I get a burst of acknowledgments back, it's not going to happen. So I'm still clicking on send, guys, and you can probably hear the clicking in the background. So this stuff goes in bursts. You see that? There's no way to kind of avoid that. Very interesting, somewhat unintuitive behavior. Okay, moving right along. When TCP begins, how does it know what window size to start with? Well, it has a guess as to how much you can send in a window before you're going to be getting close to being caught, close to having a dropped packet. Well, what does close mean to having a dropped packet? The way TCP works is when it says that you're close to having a dropped packet, what it really means is that I've looked at all the exponential values and looked at the past history of the things that I've experienced, and my losses have been in this range right in here. So therefore, I'm going to set a flag here because this is the next exponential jump. If I were to continue to grow, and I'll explain more about what this means in a minute, here's where the danger zone kind of is. So once I get to this point, I need to implement this sort of step-by-step growth. So let me extend the child analogy a little bit. The kid doesn't get out of bed and start tiptoeing right from there. The kid gets out of bed and runs all the way to the top of the stairs. That's when the tiptoeing begins, because that's when there's the risk that you're going to get caught by your parents being out of bed. So you can go quickly for a while, but then when you get to a point where you think you're close to running into trouble, then you'll need to slow down and kind of inch your way, inch your way carefully. So that's going to happen in this window here, and you'll notice it's a power of 2 factor, 1, 2, 4, 8, 16. So the way TCP slow starts works is they have this number in mind. They know what this number is right here. It's been set by the operating system at first. So I can send 1 packet. I can set my window size to 1 and send 1 packet and get 1 packet back. That part I can do. And if I get the acknowledgement back and everything's okay, great. Then for every acknowledgement I get back, I will grow my window by 1. So I get 1 acknowledgement back. My window size had been 1. Now it's 2. So I can send a window of 2 packets at the same time. I get one of the acknowledgments back, it's 3. I get the other acknowledgement back, it's 4. But these things happen in bursts, as we just saw in the simulator. So my window size really is immediately 4. So maybe I start sending 1, 2, and 3, but it immediately goes to 4 before I'm done. So I send 4. 1, 2, 3, 4. And those 4 come back. And when the first one of the 4 comes back, I go to 5, then 6, then 7, then 8. So you see what I'm doing? 1, 2, 4, 8. I send out 8. I get 8 back. I'm at 16. And now I've reached that point where I had that warning from the operating system that I'm getting into danger mode. So what I'm going to do starting at 16 is grow 1 by 1. I will send my 16 back. That's fine. And I'll get acknowledgments back. But now every time I get my whole window's worth of acknowledgments, when that whole thing is done, I won't be at 32. I'll be at 17. I'll be at 16 plus 1. I'll send 17 out. I'll get 17 acknowledgments back. When that whole thing is done, I'm not going to be at 34, which would be double. I'm going to be at 18. And then I'm going to send 18 out, and I'll be at 19. At some point, probably, I'm going to get into this danger zone, and I'm going to have a lost packet. And when that happens, I'm going to take whatever size I'm at the moment, cut it in half, and set that to my window size. So let's suppose my window size is 19 when I have a loss. I'm going to take 19 divided by, stop it, overlay little dialog box, 19 divided by 2. And to be conservative, and this will be a point of confusion for you. You'll see us do it both ways in the book and on the simulators and things like that. It just drives me insane. But you can either make this 9 or you can make it 10. If you want to be conservative, make it 9. Half and then round down. So I'm going to send 9. And when I'm done with those 9, I will send 10. And then I'll send 10, and I'll continue. So that I can continue on up to 50 this time. Hey, there's no limit. If I have a loss at this time, then I'm going to cut it back down to 25. Right? So that's going to be my congestion window size. So if I look at what's going on, this looks a little different than the sawtooth. I start off at 1. I went to 2, 4, 8. Drawing that a little too aggressively. I have 1, 2, 4, 8, 16, and then I had 17, 18, 19, 20. I cut it in half. I grew some more. Linearly, I cut it in half. I grew some more. I cut it in half. I grew some more. I cut it in half. This is the sawtooth part. This is before that. So there's names for these 2 modes that TCP goes through. The first part is called slow start. You will set your window size to 1. With every acknowledgement, you will add 1 to your window size. So if I get 2 segments sent and 2 acknowledgments back, I add 2 to my congestion window size. So that will grow exponentially. It's slow at first, but it ramps up exponentially fast. That turns out to be way too conservative for some people. Like if you are Akamai, you have your own content delivery network, and you know there's no congestion. You own every hop. There's no contention. You know exactly what's going on. Why not start with a window size of 1 million if that's what you know your network can handle? So this has some detractors and some people that have kind of rewritten it to try and avoid some of these issues. All right, so that's slow start. there are names given to the various releases of TCP that occurred over the years that coincide with the name of the release of the version of Unix with which they were bundled. And Unix in those days used to be distributed by the University of California at Berkeley. And AT&T owned Unix. They gave the University of California at Berkeley permission to distribute a essentially free version of Unix, but only to nonprofit and educational institutions. So we used to have to sign a contract with the regents of the state of California, of the University of California system, if you can believe it. And then we had a license agreement to get that copy of Unix. If you were a commercial institution, you had to license Unix from AT&T. So the Berkeley version was called Berkeley Standard Distribution, or BSD Unix, and the AT&T version was called System 5, which was a reference to the 5ESS electronic telephone switch for which it was designed to operate. All right, so TCP came out with Reno pretty early on. That was the name of BSD that was of Unix that was being distributed, and we sort of threw it in there with that. And one of the things that TCP Reno will do, because it was more advanced, it wasn't the first one that we did. We did TCP Tahoe before that. TCP Reno got smart, and it would look for not just timers going off to figure out that something had been lost, but it would look at those duplicate acts. So I'm going to go back and show you the duplicate acts again with the go back N protocol. So you'll remember with the go back N protocol, if I'll send another one here. I'm going to drop packet 1 and resume and send some stuff. And they keep sending me back the same acknowledgement number. I got it once. I got it a duplicate one time, a second duplicate, and a third duplicate. When this third duplicate shows back up, I'm basically going to know before the timer goes off that the network is working because I am getting acknowledgments back. So clearly the other side's getting some stuff, it would seem. And that guy is probably dead and gone. The packet 1 is probably never going to make it. Lots of other packets have made it, and I've gotten some acknowledgments back. So wake up, this guy is not coming back. So, but look how long it takes for this service to realize it. I've received my triple duplicate ACK, but if I wait for the timer to go off, it's going to take a long, long time. In the meantime, I'm kind of hung up. All right, so that's what getting duplicate ACKs will mean. So Reno improved on what we had with what I just showed you by when it sees a triple duplicate ACK going ahead and sending it. TCP Tahoe, which was the predecessor version, will not basically react the same way to that. The other thing TCP Reno does is it won't freak out and cut the window all the way back to size 1 and start over again. It'll just cut it in half, just like I showed you a minute ago. But there were versions of TCP that would go all the way back down to basically 1. Like, oh, we've dropped a packet. Let's like stop sending anything at all and go all the way back to 1. Too reactive, but understandable. It was perfectly understandable at the time. So we end up with some really cool graphs out of this stuff. One of them is switching, when we switch from slow start to this growing linearly. And that number that the operating system said, which was the hint about when we should expect problems to occur, is a threshold value of sort. And it's called the slow start threshold. And that's when, before we get slapped in the face with a loss, which could happen at any point, it could happen down here as well, but the odds are better that it won't. So when we get to the threshold, we'll stop growing exponentially. We would have grown to 16 here after all. Instead, we grew to 9. So we'll start growing linearly instead. And the difference between two of the very many releases of TCP, Reno and Tahoe, is when Reno sees a loss that it assumes has happened because of a triple duplicate ACK, it has some confidence that the network at least is working okay, and it won't drop the window all the way back down to 1. Tahoe will. It will always drop the window back down to 1. And both of them will do that when the timer goes off. So this more conservative of just cutting it in half is only afforded to us by Reno when it sees the network is still working. A triple duplicate ACK occurs. If you're not getting triple duplicate ACKs and the packet really was lost, then the network is kind of down because you should be getting at least duplicate acts. There's other reasons when that won't happen. Like, what if the packet that got lost was the very last one in a window, or the very first one? You could come up with some base cases that sort of complicate things, but generally speaking, this rule works well. So the threshold is variable. So what we see happened here is I was at 12, a window size of 12. One of my segments in this 12 got dropped, and I had 3 duplicate acts that came back to tell me what was going on. So I'm going to cut my threshold in half to 6. You see that happens. So my threshold value gets redefined always to 1/2. My window size, which is not the threshold, my window size will either be reduced to match it, or it will be dropped all the way to 1. But either way, my threshold is now 1/2 of what it was when I had the problem. So now my danger zone is in here. So now what I'm going to do is grow myself exponentially, but not past my new threshold, not past 6. And at that point, which was lower than it was before, at this point I'm going to start growing linearly. Now I think if I'm going to have a good day, I'm going to have some luck here, because I'm going to look in a folder and in some tools, and I'm going to have a TCP byte count slow start graph. That doesn't sound quite right. Let's see if it opens it up, though. I'm ever the optimist. So let's see what this one does. There's a V2 out there that has a earlier date. Not quite sure I had pulled that off. But let's see what this guy does. Okay, that's not the graph exactly, but I know exactly what this is showing me. Yeah, this one's not the graph. Byte count. Do I have a graph in here still? I may be unlucky today after all. This one says it's the freaking graph though. Why do I not see a graph? I've perpetually tried to write code, only in Excel, mind you, that lays out what the TCP graph will actually look like. And I may not be able to do it. Well, fear not. There's a randomized place to get this done that's fun, and I will show you. And I think it's here. Here we go. I think it's this one. It sure is. So here's my window. I have some of this that's exponential and some of this that's linear. So it's a little hard to see, but because I don't draw the lines everywhere I want. But here I started off with the window size of 1, then I went to 2, then I went to 4, then I went to 8. And then I had a loss that took me down to 4. It looks like my threshold was 8 to begin with, so I was as far as I was going to go anyway. But it was a triple duplicate ACK. I know that because I didn't cut my window size in half. And for reasons that we'll describe more later, I'll just have to tell you now that the triple duplicates I add back in. So I go from 8 to 4, but then I add the 3 duplicates back in, 5, 6, 7, so my window size is back to 7. It's almost the same as it was before. Then I get up to 11. I have a real loss that goes down to 1. Then I get up to my 11 was my threshold, so 5.5 plus the 3. Here's where my next one is. I have another loss of 1. I grow linearly for a great deal of time, and then I finish. If I want another problem like this, I click here, and I'm shown another one. Lots of losses in this one. This guy's having a bad day, so I'm going to shrink this down so I can read the text again and do another problem like this and see if I can get some that are a little more interesting here. Lots of losses here, which kind of sucks. I don't want to buy. Okay, here we go. These are triple duplicate X. So you can see I lowered my window, but not as aggressively. Only when I have a full loss. Here was a triple duplicate, loss, 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 loss. You know, what's up with that? You don't have that many losses in a row like that. All right, so there is a tool, and I'll give you a homework to kind of go through this. That'll walk you through a little bit of that. But again, to recap the variables, you have your window size, which is called congestion window. It has the variable, let me get this out of the way, it has the variable name CWND. God, that's a bloodbath. All right, so let me move this over, and we'll write these variables down. I'm going to shrink this back some so I have a little more room and a little more drawing space. CWND is my window size, and it changes with every transmission, potentially. I will grow exponentially first. Exponential growth is called slow start. Once I reach a special variable called my threshold that says you're getting close to getting yourself in trouble, that variable is called SS threshold or SS thresh. Got the threshold, that means I'm there. Then I will start growing linearly. And when I have linear growth, I'm what's known as in CA mode, which stands for congestion avoidance. Not on the diagram, but that's what it's called, CA, congestion avoidance. When I have a loss and I drop down and try and pick a new window size again, depending on the nomenclature, we'll get a little bit more into that. You know, you have after a loss, and you're going to set your window size either to 1 or 1/2 of CWND, what it was when you had the loss. That's called fast recovery. FR. All right, so some variables. CWND, slow start, threshold, congestion avoidance, fast recovery. Right, so that's what will govern the world on these diagrams. All right, let's take a look through congestion control. I start off with no particular reason, no action. I set my window size to 1. I set my threshold to 64. And you'll notice it's 64 kilobytes. Remember, we're always counting bytes. We're going to use the illusion that we're counting packets, but in the background, we're really always counting bytes. So I start off with here, and if I get a duplicate ACK, I increment the counter. If I see 3 duplicate ACKs, then I'm going to retransmit something. If I get a new regular ACK, though, I will set my duplicate ACK to 0, and I will add the number of bytes that are in a normal packet to the size of my window. So that's going to have the effect of adding one more packet. All right. If my window size is on greater than my threshold, then I can't send any more. My window's full. Oh, that's not true. If my window size is greater than my threshold, then I should not grow exponentially anymore. I should start growing linearly. I'm going to blow off the math for now on how we do that. I'm just going to tell you that's what's going to happen. You enter into this scheme right here, and you start growing one by one. And you start looking at duplicate ACKs again as well. If you ever get a triple ACK, then you're going to retransmit the segment, but they haven't exactly shown that here. What they've basically shown is what happens when a timer goes off. And when a timer goes off, it's bad news, whichever mode you're in. If a timer goes off, you set your window size all the way back down to 1, and you cut your threshold to 1/2 of the window size you were at when the loss happened, and you move on with your day. Okay. Duplicate ACKs that are triple in nature from either side, the slow start or the congestion avoidance side, if you get a triple duplicate ACK, then you're going to retransmit and set your window size to 1/2 of the threshold, same thing as the new threshold value, one size the old window size, and continue on. So we'll go into this in more detail and after spring break. I don't expect people to remember this, but I kind of want you to see the 3 names of the states here: slow start, congestion avoidance, and fast recovery. Fast recovery is what happens when you get a triple duplicate ACK. If you get just a plain old timeout, you go all the way back over to here. You start off again from kind of from scratch. So when the timers go off, things are bad. When a new ACK comes in, you're happy. Okay, what is the average throughput that we get out of a network that behaves this way? Well, remember I told you you're going to get between the full bandwidth you can have and half of that. because we alternate you when we look at these. When we look at these exponential numbers about how you're growing, not that one, that one. We're growing exponentially, and I told you the danger zone was in here somewhere. So it's between 16 and 32. You know, this is potentially your maximum amount of bandwidth, but you're going to float between that and this. And you'll tune this thing up. It won't always be between 16 and 32. It could be between 15 and 30 or something like that. So if this is your fair share, if there's the total amount of bandwidth and your window size is basically W, then you're going to be cutting it in half and growing back up to the window size, and cutting it in half and growing back up to the window size. So what's the average amount of bandwidth you're going to get? Well, this tells you it's 3/4 of the window size. Well, you can see that with your own eyes. You don't need this thing to tell you that. Oh, stop. So if I paste this in, and I ask you to draw a line down the average, you can do that. The average line is going to basically be right down the middle, right? And what is that? Well, as luck would have it, it's about 3/4 W between W half and W full. So you are going to get about 3/4 of window size through on average. You're going to vacillate between those things. That's your average throughput. 3/4 your window size, your maximum window size. All right, that's all we've got for today. The rest of this we kind of go through in more details and start adding other users into this. We will come back and re-review a fair amount of this after spring break. But I hope you guys have a great break. Get some rest, and I'll see you 2 weeks from Monday, or a week from Monday. Bye, everybody. Okay.